So lesson 8, motion with several speeds. We want to introduce the concept to you of relative velocity. Relative velocity. Jordan, how fast are you traveling right now? Not as a number? Jordan says he's traveling 0 meters per second. Is he correct?
Yes.
William?
Depends on how technical we're being.
Okay, depends on how technical we're being. He's right. Is he correct? Yes and no. It depends on what we're comparing his velocity to. It depends on relative to what other objects we're comparing his velocity to. Compared to the room, what's Jordan's relative velocity? 0. Compared to BC, what's Jordan's relative velocity? 0. Are you really standing still, though? What if we compared Jordan to the sun? What if we said relative to the sun?
You're always moving.
Okay, you're always moving because there's two things. The Earth is spinning, and it's also moving around the sun. In fact, you're traveling actually at a pretty good clip. If you're bored, sometime you can crunch the numbers. But if somehow a big invisible monster or whatever grabbed the Earth and stopped it instantly from spinning, you would all fly into... Which wall would you go flying into? The east wall or the west wall if the Earth suddenly stopped spinning and your momentum carried you forward? Think about it. Which wall would you go flying into? I'm asking you to figure that out by thinking about what you know about the sun and daylight and hours. Would you go flying into the east wall or the west wall? I think we can agree you're not going to go flying into the north or south wall because we're pretty sure the sun moves from east to west. So if the sun moves from east to west, appears to move from east to west because it really doesn't, which way is the Earth spinning? I think from west to east, right? The sun is standing still. I'll face the same direction as you guys. So the sun is standing still, and let's put, which way is east for us? Right. North is that way? East is that way? West is that way? So if the sun appears to be moving this way, it's because the Earth is moving that way. So we're all moving this way, all of us right now, relative to the Earth. And if a giant suddenly stopped the Earth, all of us would go flying into that wall, and pretty fast. You can actually crunch the speed, but you need physics 12 to do that. Fast enough, we'd all die. Why aren't we feeling it? Because relative to the Earth, you are standing still. So when we have relative velocity, when we have two objects moving, it's often convenient to determine their relative speed. For objects going in the same direction, this will be the difference between their speeds. For objects going in opposite direction, the relative speed is the sum of their speeds. Say what? It's easier from a picture. Example 1. Suppose I have object A and object B, and they're both traveling at 40 kilometers per hour. Relative to each other, how fast are they traveling? What would they see each other doing? Would they see any of them getting further away or any of them getting closer to each other? So Michael, relative to each other, what's their relative speed? 0. Kilometers per hour. We're going kilometers per hour because we're thinking in terms of cars, because that's what most of you have the most familiarity with objects traveling at different speeds. What about this second situation, the one on the right? So once again, here's object A, here's object B. What does object B see? When it looks at object A, how fast does it see object A traveling? Sees A at 20 kilometers per hour. What does object A see? And let's assume that we're all traveling forwards in this picture. What does object A see? AJ. To object A, it looks like B is slowly backing up towards him. Right? Right? So relative to object A, B is traveling negative 20 kilometers per hour. Which one's right? They both are. There is no right answer. This is part of what Einstein was talking about with his theory of relativity, where he was saying, look, there is no one right position that you can say, here's 0, 0, and everything is correct in terms of that. Because, by the way, is the sun moving?
Maybe.
Absolutely it is, because the sun is spiraling around the Milky Way galaxy, and the Milky Way galaxy is moving around in the universe. None of us are standing still, folks. But you know what? We ignore that, because what Einstein said is, as long as you're all using the same relative speed, the laws of physics will be the same for all of you. It'll work. What about the third situation, situation C? So here's object A, here's object B. What does object A, well, let's do object B first. What does object B see A approaching at? 60. Object B, see, I don't know if you ever imagined this when you're driving in a car, but next time you're in your car, you can use your imagination and just imagine that you're standing still and the earth is spinning underneath you. And some cars are moving forward very slowly compared to you, not at 110 kilometers an hour, maybe only at 3 kilometers per hour. And some cars are moving backwards towards you. You're reeling them in because you're standing still and the earth is spinning underneath you. That's kind of what we're talking about here, that little imagined state. So yeah, object A and object B would both see the other vehicle coming towards them at 60 kilometers per hour. That's a 60 kilometers per hour. That idea allows us to deal with objects traveling at more than one speed. If we have two objects traveling at different speed, Tanisha, we're going to say, forget it. Pretend one of them is standing still and use the relative velocity and then all of our dVTA equations with the relative velocity. For example, example 2, we have two trains. How long does it take these two trains to completely pass each other? Okay, I'm going to zoom in a little bit. First thing, I think to completely pass, if we were timing this, Andrew, we would start our stopwatch click when the front got right to here. We would stop our stopwatch when the back gets to there. That's the definition of passed. You start passing when your front end touches someone else's back end. You finish passing when your back end leaves them in the dust. Is that okay? So here's my question. I saw a whole bunch of you draw that arc. Instead, I'm going to erase it and I'm going to say, that's the total distance the back end has to travel in order to pass. See it, John? What is that total distance? I think you can figure it out by looking at the trains. Okay. We're going to have a distance that we're traveling of 250 meters, which you'll notice, William, does not appear in the question anywhere. We have to reason that. We have to say, you know what, our definition of passing is going to be start it when the front end touches the back end, finish it when the back end leaves the front end in the dust. How fast is the bigger train traveling? 13. How fast is the smaller train traveling? 5. No. What's the relative velocity? I'll call that VREL. 8. I think we're going to assume that A is 0, acceleration is 0, because it doesn't seem to indicate there's any kind of changing acceleration. So my question is, what do they want us to find? I'm looking for an equation that has d, v, I guess A is 0, it can have A in it, and t.
Would that be VI?
Elijah, what's your question? It's a good question.
Would that be VI or GI?
What's acceleration? So if acceleration is 0, isn't VI the same as VF, the same as V average, the same as V, the same as V? So you know what? That's why I said I'm looking for an equation that has d, v. I didn't give you a specific, because either one of those will work, because final is the same as initial. It's got to have t in it. And if it has a, that's not a big deal, because a is 0. I think we're going to use d equals VIT plus a half AT squared. Yes? But you know what, Dylan? We're going to use the science 10 one. Because a is 0, I think we're just going to use, because the half AT squared is going to cancel. Why? A is 0. How would I get the t by itself? Yeah. T is going to be the distance divided by the velocity. What's the distance the train is traveling? 250 divided by, what's the relative velocity? 8. 250 divided by 8, that's going to be the same as 125 divided by 4, which is going to be 25 plus 25 divided by 4, which is going to be 31.25. Double check me, I could be off. I got it to 3. Ooh, Mr. Dueck. 31.3. How many sig figs? 3 sig figs, 3 sig figs, 3 sig figs. 31.3 seconds. That's an example, Callum, of where relative velocity can make what otherwise would be a very, very difficult task, trying to keep track of two velocities and two... actually, it fell apart when I said, just let the slower thing be standing still. Or let the faster thing be standing still. Let one of them be standing still. Usually the one that's doing the passing, we pretend that one's moving, and the one that's getting passed, standing still. So I wrote underneath here, solution. I walked you through what we just did. So since both trains are moving, this seems like a difficult task. The longer train will catch up and then pass the shorter train, but we don't know how far both of them will travel during this time. So I've walked you through what the goal is. Let's try example 3. Oh, trains facing each other. How long does it take for these two trains to completely pass each other? And I did give you the answer this time off in the margin. 28.8 seconds. Let's see if we can prove it. Okay. First thing I want to figure out is how far a distance are we actually talking about? I think our definition of they've passed each other is going to be when this back end here passes that back end there. Is that okay? Because now they're coming towards each other. So instead of saying when the back end passes the front and moves away, now we're saying they pass each other when there's nothing opposite each other anymore. How far are we going to have to travel, starting right now, to accomplish that? Well, how far is between the trains? 260 meters. How long is the first train? 120 meters. How long is the second train? 80 meters. How far are we going to have to travel? Can you see how we can crunch the numbers? How long is that distance? 400 and what? 460? 460 meters. The distance that we're talking about traveling here, 460 meters. Okay. Again, Elijah, we're going to assume A is 0. They want us to find T. Okay, fair enough. I need a velocity. The clever thing to do is to pretend one of these trains is standing still. I'll pretend, oh heck, that this guy is standing still. And that this guy is going to travel 460 meters on its own. Mathematically, that's what's going on. So I want to use the relative velocity between these two trains. What is VREL, the relative velocity between these two trains? 16 meters per second. (16 meters per second). Once again, we can use get the T by itself. we're going to get, well, they got 460 meters to cover divided by 16. What is 460 divided by 16? Do this one in your head, Mr. Okay, fine. It's going to be 230 divided by 8, which is going to be 115 divided by 4, which is going to be 25 plus 28.25? 28.75, yes, I'm sorry. 28.8. Yo.
For the V route,
Yep.
they're like going towards each other.
Yep.
You add them, and if they're going the same way, you subtract them. Is that how you find it? Or?
Let's see. For objects traveling in the same direction, this will be the difference between their speeds. Difference, is that a math word for subtract?
Yeah.
And for objects going in opposite directions, which means towards each other or away from each other, it will be the sum. Yeah, sure. That works. Glad you figured that out. Hey, let's add a part B. Here's a classic one you may have heard before. Instead of asking when they pass each other, suppose they're on the same track and something has gone horribly wrong. When do they collide? Moi. Ha. 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 Okay, okay, we went through the bill and laugh there. Actually, Sean, it's the same question. The only difference is how far we have to travel. How far do they have to travel before their front ends hit? 260. That's the only difference. Well, D is going to be 260. V is still going to be 16. T is going to be distance divided by V. It's going to be 260 divided by 16. It's going to be 130 divided by 8. Elijah's trying to do the math in his head. I can hear him murmuring over there. I like it. What do you got? 16.25? Go 16.3 seconds. Oh, if it takes 28.8 seconds starting right now for them to pass, and they'll be level with each other 16.3 seconds in, I guess the actual passing part when the trains are speeding by each other would be 28.8 minus 16.3, 12.5 seconds. That's how long you'd hear the trains going by each other. I think it's helpful to have an idea of what's fast and what's slow. I do this all the time in Physics 12 especially, because AJ, it's nice if you can, when you're doing a number, your calculator, you can glance at it. That's wrong. You know you made a calculator mistake. So we're going to mix and match some speeds. I have a list of about 10 speeds: human walking, fastest animal running, top fighter jet, light, etc. And then to the right, I have a bunch of the speeds. Let's see if we can mix and match which ones go with which. I always start out with the extremes. The fastest and the slowest. Is there anything on this list that you know is either the fastest for sure or the slowest for sure? Light is the fastest. What's the biggest number that appears over on the right? And let's cross that one off. What do you think the next fastest thing here is? Fighter jet or sound? I guess a fighter jet does break the speed of sound, doesn't it? So what's the next biggest number over here? And we got to be careful because some of these are in meters per second and some of these are in kilometers per hour. Right now for the fighter jet, I'm either looking at the 3,600 kilometers per hour or the 330 meters per second. How fast is 330 meters per second in kilometers per hour? It'd be nice if Mr. Dewick had given you a quick, easy trick to convert from. Oh yeah, it had something to do with 3.6. Multiply or divide? I think you times by 3 point. Sorry?
1,188.
Okay, so the 3,600 is the fastest one? Is that what you're saying, Andrew? It's faster than 330 meters per second? Say yes. Yes? Then, okay, I think the top fighter jet goes, which is true. They can hit about 3,500 kilometers per hour. Let's cross that one out. All right. What's the next one? The next fastest one is Formula One race car. I think I disagree. I think I disagree still. I think sound, because cars don't go faster than sound. Okay? And actually, sound I have memorized. It's around 330. In fact, it's around 333. It's actually 340, but I remember sound is 333 meters per second, because that's an easy number for me to remember. It varies. It depends on the temperature, and it depends on the altitude, and it depends on the weather, how much moisture there is in the air. But sound in the air generally, 330, 340 meters per second. How fast what's the speed of sound in a vacuum? Ooh, William, back row. Yeah, no sound in a vacuum. Sound needs something to propagate through, to transfer itself through, because it's a wave. In a vacuum, you got no substance, doesn't work. Okay, next fastest one. It's either a Formula One race car or terminal velocity human. Well, how fast do you travel on the freeway in kilometers per hour? 100. So Formula One race car, do you think they'd go about twice as fast as on the freeway? Okay, so I'm looking for a number about twice as fast as on the freeway, I think, for a Formula One race car. I'm looking at that 220 kilometers per hour, I think. Next thing. Well, you know what? The very middle one there, I know this because I have my license. What's the speed limit for a car on a city street? 50. Okay, let's use that. Any of these other ones you want to take a stab at?
Terminal velocity.
Yeah.
10 meters per second for the fastest human running. Because 100 meters is done.
Yeah, Usain Bolt runs the 100 in just under 10 seconds. He's starting from rest. So let's assume, yeah, I think around 10 meters per second for the fastest human running.
55 meters per second for the animal.
55 meters per second for the animal? I don't know. See, I don't have a good handle on how fast that is. Okay, which animal are you talking about?
Cheetah.
How fast does a cheetah go, not in meters per second? Do you know any other units?
Like 100.
See, I know it hits 60 miles an hour because I grew up in the pre-metric system. Yeah, I think it hits 100 kilometers per hour. It hits freeway speeds. I think I'm looking at 100 kilometers per hour for the cheetah, for short bursts. So I'm going to go with that, I think. Fastest animal. Oh, and I forgot to cross off the 10 meters per second. Well, I think now we've narrowed it down. Which of those do you think is terminal velocity? I'm pretty sure it's 55 meters per second because I'm telling you, when I jumped out of an airplane, if I hit the ground at 4 kilometers per hour, I'd be just fine. I'd be sore. I'd be fine. And 4 kilometers per hour. You know what? Just so we can compare these a bit better, over here on the left, I'm going to put either the meters per second equivalent if it's in kilometers per hour, or the kilometers per hour equivalent if it's in meters per second. So get out your calculator, because this is the one shortcut that is worth memorizing. Meters per second, kilometers per hour, it has to do with 3.6. Which one? Do you times or do you multiply? So 4 kilometers per hour, how many meters per second is that?
1.1.
Is it, or is it, you travel 14.4 meters per second if you're going 4 kilometers an hour, or 1.1 meters per second if you're going 4 kilometers an hour? And I think I've said this before, but here is how I remember it. I always go back to the speed that I am familiar with because I have my license. Freeway. What's the freeway speed in kilometers per hour? Because it's also a nice round number. What is it? 100. So there's two possibilities. 100 kilometers per hour could either be 360 meters per second, or it could be that. I'm not sure, Perry, do I multiply or do I divide? But I've been on a freeway. Have you? Okay. If this first one was correct, you've been on a freeway, do you go 360 meters every second? Do you pass 3.5 football fields every second? Okay, that's how I still fall back on this. If you ever ask me, how do I go from meters per second to kilometers per hour, you'll see my eyes glaze for a second. And Tanisha, what I'm really doing is I'm going, well, 100 times 3.6 is 300. That's way too big. So from kilometers per hour, it's divide. From meters per second, it's times. I've never bothered memorizing it because I can always figure that little step out for once in 1 second in my head. So what did I say? Kilometers per hour, it's divide. Is that right? Is that what we said? So 1.1 meters per second. 3,600 kilometers per hour. This is what a fighter jet does. They're traveling about 1,000 meters per second, about a kilometer per second, which is why one of the things they teach fighter jet pilots is don't look in front of you. You look way in front of you because by the time what's in front of you gets to your plane, you can't react that fast. You're looking several miles, several kilometers ahead. And even then, you better be reacting fairly quickly. Which other one? 50 kilometers per hour. 13.9 meters per second. 220 kilometers per hour. 61.1 meters per second. And I got 100 kilometers per hour. Oh, I did that one already, but I erased it. 27.8 meters per second. And let's do the meters per second into kilometers per hour. 10 meters per second, I times by 3.6. That's going to be 36 kilometers per hour. Oh, I forgot to do, light is kilometers per second. Light is 3 times 10 to the 8th meters per second. That one I have memorized. 330 meters per second, so for 330, I times by 3.6. Is that what you guys said? Is that right? Yeah, it was times by 3.6. So sound travels, what's a nice round number fairly close to that in kilometers per hour? In fact, you know what? If I'm doing nerdy math in my head, I don't even use 1,200. What's a really nice round number really close to that? About 1,000. So when you hear lightning, for example, when you see lightning and you're counting to hear when you hear the thunder, every second is about 1 click, give or take. 1.2 kilometers if you really want to be fussy and do some good math. But yeah, what do we say? I'll go put 1,200. And 55 meters per second. How fast would I have hit the ground at? I'm curious. 198. It's about 200 kilometers per hour. Well, let's do the exact value, Mr. Dewick, since it worked out evenly. Gives you an idea of what's really fast, what's pretty fast, and what's not too fast. So, turning the page here, I think I did some of this with you in a different set of notes already. So I think we can say, that's a stretch, Riley, good stretch. We already did that. Motion with several constant speeds, I think in lesson 4. We already did that. We already did that. We already did that. We already did that. Hey, this is kind of fun. We already did that. This is kind of fun. We already did that. This is important, so you want to make sure you know that. I'll circle it one more time. We already did that. We already did that. Do I have some relative velocity questions on here, Mr. Dewick, or what? No, Mr. Dewick. Let me pause my lesson for a second. I need to get you more your homework is not from this. I gave you this homework already. I have some relative velocity homework, and it doesn't look like for some reason that it's on this. I'll have it photocopied for you for Tuesday. We'll do one more example on Tuesday as well. So your homework right now is to finish both the take-home quizzes, and I'm probably going to give you a kind of a unit review thing to get you started as well.